Hey there, hi there, ho there. Welcome back. This is Unit 9, Faults and Folds. Kind of coming full circle in the rock cycle, no pun intended. As we last talked about metamorphic rocks, heat and pressure are necessary for those, and because of said conditions, you can also get faulting and faulting. Folding and faulting, excuse me. And this kind of makes its way back into the plate tectonic cycle as a large driver of all of this. But let's jump into it, shall we? So let's talk about rocks that are under pressure. Under pressure. Stress. Oh my gosh, I'm so stressed. Well, in geology, it has kind of a specific meaning. Stress is the force acting on a surface. It may be greater in certain directions than in others, but we need stress to cause movement of rock material to create faults or to create folds in rocks. And you can kind of see that the layers of these rocks here in these mountains have been all kinds of folded up. It might be a little bit hard to see in this image, so there'll be additional information on that. But there are different types of stress associated with different directions of stress. So types of stress include, let me get some Play-Doh out here, attentional stress, which is a type of stress occurs when rocks are being kind of pulled upon, and you can kind of see the direction here. So you have some sort of rock, attentional stress will pull on that rock. You have a compressional stress, so kind of a force inward towards one another. So we can take a rock and compress it, compressional stress. And then you get a shear stress. This acts in opposite directions, as they all do, but kind of in a side-by-side motion parallel to a surface. So kind of moving kind of opposite directions parallel to a surface. All right, here's a little bit better image of it. So depending on the direction of stress, we can see that manifest itself differently in these different types of faults and folds. So stress causes strain. Stress is the name of the force being applied to a rock unit. The strain is a change in shape or volume of a rock in response to stress. So for instance, I'm applying a compressional stress to this Play-Doh and I'm causing a strain. I'm changing its shape and possibly its volume as well. All right, so stresses cause strain. Now, what we see in this chart here is stress versus strain. So the more stress, the more force, the material acts differently. Rock material, believe it or not, can be considered sometimes plastic in that it can bend, but it can also break. So, a little quick physics here. So you have something called Hooke's law, and Hooke's law is kind of related to the elasticity of different objects. Whether you can see it or not, objects can bend. Rocks can bend. So as we bend something, if we apply a little bit of stress, we're in an area called elastic deformation, which is reversible. I'll show you an example of this in a little bit. But there's a point where we can apply so much stress that the elastic limit is reached, and we can cause a permanent strain, and that's ductile deformation. That's irreversible. So we've applied so much stress, now this strain manifests itself in a change in shape that cannot be reversed without some sort of additional force. As we continue to provide stress, at some point the material will break or fracture. So all material can bend to a point and snap back, or bend to a point, not snap back, or bend so much that it fractures. So kind of three areas: elastic deformation, ductile deformation, or fracture. So for instance, elastic deformation. Elastic deformation is just a temporary change in shape from which material rebounds after the stress is removed. So let me blow me up real quick. So here is just a paper clip, kind of regular. I'm going to put my finger in here. You can see the stress of my finger. The force I'm applying is spreading the paper clip apart to provide a strain, but once I remove that stress, it just snaps right back. So that's elastic deformation. There's a change, but once that stress, that force is removed, that change, that strain goes away. So that's elastic deformation. You think about elastic rubber band or the elastic on your undergarments, right? It snaps back once you let it go. So that's elastic deformation. And then we have something called ductile deformation. That's where the elastic limit is exceeded, so a little too much stress causing a little too much strain, which results in permanent change in shape from which material does not rebound after the stress is removed. Again, going back to the paperclip as an example. All right, if I apply enough stress to this paperclip, I keep applying a stress, shut it right in there. I've exceeded the elastic limit. It is now in the realm of ductile deformation. It has changed shapes. I've removed the stress, and it's not going back. All right, it's not going back. So that's ductile deformation. Ductile deformation. And I'll say it one more time just so you can see. I'll even hold it in front of this fancy whiteboard here. So that's ductile deformation. All right. And then finally, I'm sorry, and then you can see in this rock how it's kind of been squished and kind of folded up. That is ductile deformation. This rock has been folded up a little bit. These layers have been folded up a little bit. They haven't broken. They've just kind of been squished. Ductile deformation. And then we have one more, brittle deformation. So brittle deformation is a permanent change in shape in which a material finally breaks or cracks. That a little too much stress has caused too much strain and the material can't take it anymore and it will break. Rock layers will do the same thing. To a point, they will bend, but at some point, too much stress will cause it to break. So but what's interesting is that rock that is brittle in one set of conditions may be ductile in another set of conditions. It has to deal with how warm or cold the rock is. Warm rocks will bend a little bit. Colder rocks might fracture more easily. So it comes down to characteristics of the conditions in which it's in. So looking back at the paperclip, again, we're in ductile deformation, but a little too much stress, causing too much strain, it will break. Now we're in brittle deformation. It's broken. It's broken. And you can see that in the rock layers here, how they've been broken, brittle deformation. So there are factors that affect rock deformation, and I touched on some just previously. Temperature, so how warm is the rock? Therefore, how deep is the rock? The deeper a layer of rock is, the warmer it's going to be, the hotter it's going to be, the easier it might be for it to bend. Whereas rock that is closer to the surface, a little bit cooler, might tend to break more easily. So not only the temperature, but how much pressure, how much force is being applied, how fast that force is being applied. So the rate of deformation, is the force being applied very slowly or is it happening very quickly? And then the types of rock. Different rocks have different characteristics, different strengths. Some are very tough and will bend. Some are brittle and will break quite easily. So we got to think of all these factors which go into, again, telling that story of geology. So looking at a rock, looking at a fold or fault, looking at a structure and being able to tell, well, where did this, it's not only just the type of rock, but where did this thing we see in the rock, this fold or this fault, where did that occur? How did that occur? So you're further telling that story of geology. So we'll pause here. So these are just some factors that contribute to rock deformation. When we come back, we'll talk about faults. We've touched on this back with plate tectonics and earthquakes a little bit. We will revisit that, and then we'll again further talk about folds after faults. I'll see you back here in just a minute.